A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast episode 71. I'm your host Yusuf, and for this episode of the podcast I'm very excited to welcome Lukasz Kaczmarczyk to my show. Lukasz is a senior lecturer at Glasgow University James Watt School of Engineering. He graduated with civil engineering degree specializing in computational mechanics from Cracow University of Technology. His doctoral studies were undertaken at the same institution, which he defended with distinction in 2006. His Ph.D. thesis was entitled Numerical Analysis of Multiscale Problems in Mechanics of Heterogeneous Materials. For the last decade, he is working on fracture nuclear graphite supported by EDF energy. He developed theory, numerical methods, and robust research software, MoFEM, for 3D crack propagation. In this podcast, we talked about developing and validating FEA code, open source versus commercial code, FEM for crack propagation, pros and cons of meshless methods, the research software MoFEM, and much more. If you are an inquisitive scientist and thinker and would love to learn more about upcoming projects, connect with like-minded peers, and attend live reading group sessions from experts in the industry and academia, register for free at community.sci-circle.com. To join my weekly newsletter engineeredmind.sh with more than 1500 readers coming out every Sunday, where I share weekly science insights, visit yusuf.substack.com. And now, ladies and gentlemen, here's my podcast with Lukasz Kaczmarczyk. Hey Lukasz, welcome to my show.
Hello, nice to meet you.
Very excited to have an FEA expert on my show today, and we will talk about software development for the finite element analysis today. But before we jump into the hard stuff, into the core of the finite element method, can you give us like a 1 or 2 minute crisp bio? Who is Lukasz and what are you actually doing?
Okay, I working at the Glasgow University in GCAC. This is Glasgow Computational Engineering Center. And for about 10 years, I developed code which is used by EDF and Jacobs to propagate cracks in the graphite bricks. And while I was doing that, I developed MoFEM, which is the finite element code, which has a slightly much bigger application than the fracture.
Mm-hmm. Very interesting. And we'll talk about MoFEM in a few seconds. But what I always like to ask, especially experts, is how they would define their own field. So if I ask you, Lukasz, how would you define the finite element method? What is it in the first place? How would you define it?
So this is the mathematical method for approximation some physical fields like displacement, stresses, strains, and so on. Mm-hmm. And these methods allow you to solve the partial differential equations. But of course, those partial differential equations have some physical interpretation. They can have some physical interpretation. So if they have a physical interpretation, they can solve the problems from the real world, approximate the real world problems. Mm-hmm. And if equations are correct, if your solution is correct, that means that you can make a prediction about the future, or you can learn something about the past, or learn something more about the current reality when using a finite element to simulate the experiment, because you have this additional information. Mm-hmm. But the finite element method is just a mathematical tool in the first place. I am civil engineer, but the strength of the finite element method comes that it has these strong mathematical foundations.
Yeah. When you develop software or code for finite element method in general, for the finite element method, where do you see the biggest bottlenecks? Especially, I mean, you have the equations that are set in place. Where do you see like the biggest problems when developing a FEA code?
I think that nowadays you have lots of books, resources, how to develop the code. And you have those great high-level languages that you can deploy them to solve the problem, implement the from scratch finite element in relatively small amount of time. You have, from the other hand, you have those large finite element systems. When you invest some time, you can learn about them. So this is not the difficulty just to use the finite element method or implement even it by yourself. The biggest problem is with the interpretation of the results. And I think that to understand what you're really getting. Interpretation is somehow more important than the solution itself.
Mm-hmm.
So, and this is not necessarily the easiest thing, how I observe. Because first question, you get the solution, how you can trust it. What are the error bounds for that solution? How you can check? Yeah, this is the fundamental problems, interpretation.
Mm-hmm. When you validate a FEA code, like to see if it actually gives you accurate results, is it still done in the way that you use something like a patch test to see if the FEA code actually works, or is there some more sophisticated testing behind an FEA code?
It's depending what you do.
Mm-hmm.
For example, when you work with the plasticity, for example, there are quite old benchmark tests or problems which you want to reproduce. They are not necessarily the problems from the real world, but you want to reproduce other people's solutions. And for example, necking problem, when you take the rod, it has some small imperfection and you apply the stretching to it and then is subjected to large strains, it should neck at some point.
Mm-hmm.
Okay? And then you want to capture that point and you want to capture how it's next. So this is the benchmark. So you want to first thing, you want to reproduce some other people's solution that and then of course, when you do that, you want to do it faster than others, that to get the solution in the faster way. You want to show when you get that solution, it scales better or something like that. So you still has to reproduce someone else's solution, but it has to be the same solution, but it has to be done with the smaller computational effort. But from another hand, because the finance, as we said, has these strong mathematical foundations. So there are theoretical bounds. For example, you know that a posteriori error estimator, and then in certain conditions, you should have a certain rate of the convergence. Okay,
mm-hmm.
So you can take the problem and you can try to solve it, and then you can compare this solution against something which is the analytical. That's great, and then you want to check if your convergence rate match this theoretical convergence, this error bound. Yeah, so the rate is steep enough from your method. Yeah, sometimes you can converge, but of course you can ask that. You can sometimes converge, but you can converge to something else,
mm-hmm.
and then your convergence rate can be slow. But because we're talking about the mathematics, we talk about the PDEs, always somehow, if we have error estimators, they are properly defined, you can plug in the solution and we can check whether we conserve the linear momentum. Yeah? If you have something more crazy in solid mechanics, you can check if you can conserve the angular momentum when you have some mixed elements and when you don't enforce the symmetry of the stress. So you can check certain things. Yeah. So and then you can measure the quality of it. So you have some objective ways to check if your solution is correct. Benchmark tests are okay, and typically they are associated with that to check if you have locking. Or they are associated with the checking to check if you have a stability. And then, in fact, the biggest application of the benchmark tests are problems when you have difficulties with the stability. Because the stability from the mathematical point of view is the hardest thing to prove. So if you are civil engineer like me, not always, you have this ability to prove that you satisfy in-suit condition. But much easier is to run the benchmark test. So we run the benchmark test sometimes. Yeah.
Mm-hmm. So when you run benchmark tests, it's very interesting to talk about the stability aspect. How do you even prove it? Maybe you can go a little bit more into detail. How do you prove it? Do you just do it the benchmark case and then you're done? Or do you have to do more sophisticated work on the stability?
Okay. Benchmark text only tells you that in the certain conditions, your solution is stable. But it's not guaranteed that it's objectively stable for a certain class of the problems which you want to solve with your finite element. For example, it's a classical example of Taylor-Hood element that you can apply it to class of the problems, and it will give you a nice solution. Taylor-Hood element, this is which you can use for solve the problems for incompressible materials or Stokes problem or incompressible Navier-Stokes problem. You have this when you approximate the pressure and displacement. But you can show under certain conditions this element is not stable. Benchmark test is useful that it's test that for certain class of the problems or similar problems to your benchmark test, your element is stable and it will behave well. But benchmark test itself don't guarantee that overall element is stable. For that, you need a mathematical proof, so you have to ask for help mathematician.
I see that. When it comes to building the FEA code, you have a lot of aspects, so it has to be stable, it has to be efficient, scalable, and maybe even versatile for a lot of different aspects.
But one thing that you have to just separate two things. One is a finite element formulation. So how you formulate element, and this is you can do it on the piece of the paper. And another thing is implementation of it. Okay, and this is another problem. And in that case, this is slightly different story, because the benchmark test at that point is very useful thing. Yeah, because you don't have to prove the stability of it. You want to verify if your code producing what you intended when you start your implementation. And then, so you from very beginning, this is if you look at the books about software engineering, about the programming, very often the people advise you to write the code starting from a test. So you have this unit test in your program that each time you change something in the code, over the night or automatically the tests are triggered on some development server that they are rerun constantly the benchmark test, regression test, and you're expecting always the same result over and over. Yeah. So this is the validation of the implementation. Is a different story.
Oh, okay. Thanks for clarifying, Lukasz. I appreciate it. So, what the question I wanted to ask is actually when you develop FEA code, and has to be scalable, efficient, maybe even versatile to cover a wide variety of applications. What would you say is the hardest part, or is there even a hardest part? Are all parts for developing a code the hardest?
I think that before you start to develop any finite element code, you have to ask your question, why are you doing that? What is your user? What is your target group? Okay. And then, for example, you can say, I want to write small niche program, which is used by the people doing biology and do a indentation on the cells. And this program, which I write, is a black box for them, but gives them the relation between the deformation of the cell surface and the force. So then you write that program in such a way that is well understood for you. You write, of course, the comments inside of the code that in 1 year you still remember what you have done because you cannot trust your memory, and you're writing that program differently. But you can write different kind of the code. You can, from the another hand, you can write a code for solving Navier-Stokes equations or for plasma physics. Yeah, and then you have one physics at that case. So it's a Navier-Stokes class of the Navier-Stokes problems, and then you whole structure of the code is for that single physics. And then what your only biggest concern now at that point is just You want to solve your problem as efficiently as you can. And then you have, I want to solve it as efficiently as I can on the single node computer because my potential users will use it, or on the cluster or GPU, whatever. And then you're writing that code differently. And then you're asking yourself as well the questions so then that's define your structure of the code. Yeah. And then, but different thing is that if you want to solve the problem for civil engineering problems, this is slightly different thing, because if you look at the this building, it's a messy thing, pipes, different kinds of the walls, thermal flow through the walls, deformations, fracture of the beams, reinforcement, lots of different things. So then you don't have any longer single physics. You have to write generate the structure of the code that it can handle the different physics. Mm. And it can handle different elements, different things, 1D and 3D problems at the same time. So that structure of the code will be completely different than this plasma physics code or Navier-Stokes code. And then the story goes over and over. So then first think, what is your target group? And whether they are researchers, whether they are, maybe your target group are developers of the finite element code like you. Yeah? If they are research, so for example, let me give example. Then you have a Phoenix, this great finite element code, mm-hmm. Which has this language, which allow you to write in nice, concise way, weak form of the your target group are people which knows the mathematics, know how to construct the weak form. They are not necessarily interested how you implement the integration schemes on the element or how to construct the approximation space. They want to formulate they know how to formulate the element. They know how to write the weak form for your particular finite element formulation. Yeah? And then they know how in the mathematical way define the boundary conditions. So this is the kind of the researchers. And then you can have researcher which, for example, is interested in the diffusion of the drug from the stem in your vein or whatever. So he knows that he wants to solve some diffusion equation, or she has a species and so on, so can write those weak. So, and he knows mathematics because he attended the university. And then when you study the engineering, you have definitely some course about the finite elements. And then, so he deploy for that problem Phoenix. Mm-hmm. And then you have but he's not really interested in the implementation of the finite element, mm-hmm. integration. But another example, you have a different kind of the person. You want to do, he's interested in making his more, something which sitting on the fence. He's a little bit mathematician, and he's interested in developing the numerical techniques, numerical methods. Mm-hmm. Mess with the implementation a little bit, mess with the block solver, how they work and so on, how to have a scalability. So he will or she will not choose the Phoenix. It will rather go towards the DIL2 or MoFEM code. Yeah. So different people do. Or another example, just you are civil engineer. You are interested in modeling materials, quasi-brittle materials, concrete, reinforced concrete, and so on. So you don't really interested in the structure of the finite element, but you are interested what happens at the integration points with the material. So then you will go like OFEM, object-oriented finite in developing Prague. Yeah. So then you will choose the different code. So, but you can see already, I named 3 codes, but there are many more great codes. So then, before you will start to even develop the code, you have to ask yourself the question: is your code really needed? Because if someone else is doing what you want to do, join their group, become a collaborator or even core developer, and help the community of that code itself. Yeah? So, and then you will, this is the right way, I think.
Yeah, this was very, very insightful, Lukasz. Thank you so much. What I would ask, because of, you mentioned this right now, because of joining other groups or developing other FEA codes. So would you advise people to develop their own code? Because we have had some questions coming in. Would you advise people doing software development for FEA? But what you are saying is actually join existing projects, maybe open source projects, and help them build their tool, right?
Yes, because this is when you will make impact. Because when you are really young, and then you finish in university, why people start to develop the code? And because they want to learn. They're thinking that by developing the code by themselves, they learn something. But they're learning something in the hard way. This is not necessarily the most efficient way, because you have to learn all those things, how to develop the efficient code by yourself. And probably when you will do that, you will make thousands of different mistakes, and maybe you will create bad habits, which will be difficult to remove later on. So when you're thinking about the developing code because you are starting, and then you're thinking that this is the way, I would say, no, this is not a good idea. Join a bigger group, because you will learn from them much quicker, better ways of doing that. But there is another thing. It's a hard thing. To be honest, it's a very competitive place. It's a plenty of the finite elements codes. As we said, now it's plenty of textbooks. Writing any finite element code which just works is not hard. Extremely hard. Many thousands and thousands of people can do that. Yeah. So you can, but it's a big effort from the other hand doing that. It's not the thing which you can do in the short time. So if you invest something in the developing the finite element code, what will be a real use for it? If your hard work, pays off. And to finite element code yield something, I think that you need a decade of development, to be honest, because if I look at this really successful code, like Codaster, open source, great code, they are developed for 30, maybe 35, close to 40, FEA, and then a very old code. Still is not young as well, So and then typically behind those great finite element codes like Codaster, or big developments like standing some big institution behind, or some big industry like nuclear industry, because they really need a finite element code. And this is always development of the finite element code is a long-term investment. Unless you're writing something small. As we said, this small program for biologists doing indentation, which code is designed to do one thing only very well and nothing more. Or cell force calculation or something like that. So then write this small program which is wrapped, and then it can live there in this small niche, which is only for that tiny thing.
Yeah. Let's talk about MoFEM, your own personal project you're working on. How did you come up with the idea? Can you give us like a background story why you even decided to work on MoFEM?
So about 10 years ago, we have a visit from EDF, which were working with my colleague, and my colleague working rigid body dynamics, working on the rigid body dynamics software, which enable calculate the response of the whole reactor subjected to the earthquake. In Great Britain, you don't have many earthquakes; they are not strong. But anyway, you have to take that possibility when you design or look at the reactor. And then when they visited us, they mentioned that they have had this problem with the how to calculate the crack propagating in the graphite, very brittle material. And there is a problem because the codes which they know, they cannot do that. And there was a real need from them to make up. They have experiments, they seen something, and then there is nothing which can predict what they see. And then there is another problem. This is when you're working with with something which is related to the nuclear industry. Not everything you can test easily, because not everything you can place in the lab and test, because the material is. So then the simulation is a key thing. And then we have this idea which I read a few weeks back about configurational mechanics and crack propagation with the configurational mechanics. So we said to them that we can do that.
Very interesting.
They give us a short grant, and then we start to work on it. But at some point, the initial idea is like that. So we develop for them a formulation, this method. We will show with our implementation with the research code that is working, but then the really industrial problem will be implemented somewhere else in the Codeaster, and the Codeaster will run it. But when we start to do develop the approach more and more, we start to use the methods, approximation techniques and approaches which were impossible or very hard to implement in the older FE codes with the older structure. Because FE, finite element codes, getting old. Because when you design the structure of the code, how it makes, how you store the data, where you store the data, in 70s and 80s, you will think, I have that data at the node, only. So you're creating the structure in such a way, so then everything what you have to develop with the given code, it has to fit to that structure. But now when you propose the technique, let's have a hierarchical approximation base. When I have a degrees of freedom on edges, on the volumes, on faces, and so on, this old structure is not fitting what you want to do. And this is another development in the finite elements method. The new approaches to approximate the things are trigger for new finite element codes, like IGA approximations or hierarchical approximation, fast integration with Bernstein bracing, whatever. So this is another reason, because then you find out that, okay, this is the mathematicians or some people in the paper show us that you can have this great speed or you can do these great things, but the old code is not suitable for that because it has a structure which don't predict that people will like to do that. Yeah, like example of degrees of freedom on nodes and on the volumes.
Mm-hmm. Would you say in general that when we compare like academic codes, like research codes and commercial codes, do you think there's kind of a pushback or maybe even a barrier for industries to use open source codes?
And I think this is our niche, which we find out with MoFEM, because I have seen when I write my Ph.D. I use GetFem++. Very nice French C++ code. I used a little bit FIP. I used Dolphin at some point. This is the on top of Dolphin was sitting Phoenix. And then, but But I noticed that when you have these industrial problems, civil engineering problems, the problem is that the complexity of the object which you solve, these multiple types of the boundary conditions, springs, different loads, and so on. So you have to zoo of the handling the handling of the boundary conditions, this heterogeneity of the different materials. You need some harvester like Abaqus or Ansys, which do exactly that well. But research codes like they are. This is PDE. I solving this PDE. So then in the PDE you don't mixing the volume elements with shell elements, and then you have a suddenly you don't have that thing. Yeah. So to solve the problems which struggle industry are for industry, it's this transfer from the research code to the industrial code is a real problem. Yeah. So in research code you do a proof of concept, and in the but at the end you have to implement some UMAT model or whatever, and then plug it into the Abaqus. So then this was my idea, that I want to have a FE code which using the cutting edge approximation techniques, but in the same time I can handle the zoo of the different boundary conditions. I can make a model of the building and then shake it to simulate the earthquake with everything in it. And even I have one student from Nepal. There was a few years back earthquake in Nepal, and we modeled the whole two buildings, and then we simulate how they bounce from each other, because most of the buildings were damaged not because the earthquake itself, because the space between the buildings were too small, and they start to hit each other. So then that I want to go into that direction, that my code in one single problem can handle zoo of the different PDEs, which sitting on the different elements with the different dimensions, and there is no restriction on the mesh itself, so that we can mix types of the elements. And yeah, so this was the idea.
Mm-hmm. I love that. Very cool. Anything else you would like to add, Lukasz, to that, or?
No, no. At that point, maybe. Yeah.
Okay. About the crack propagation for power plant applications, is there I would be very interested, because I've never done it. I mean, you mentioned it when you have a FEA course. You mentioned there's something like XFEM, like extended finite element method, and things like that. When you develop something for crack propagation, I would assume, and we discussed it before the podcast, there's a lot of heuristics in it. How do you develop something like this in the first place? Where do you even start for crack propagation?
Okay, so finite element method and generally approximation methods struggle with they struggle with one thing always. They can do well when you have a deformation, large, small, or even some extreme, like you have in fluids, that they even forget the deformation. They have a big problem when the topology is evolving. And when something is growing or something getting the contact, so two material points were not in contact and suddenly they are, this is where and extreme topology evolution is a crack propagation, because the D-1 object surface in volume is propagating inside. So the biggest problem is with the resolution of the discontinuity. And this bigger problem is with the resolution of the discontinuity, how to treat evolution of this discontinuity in the smooth way.
Mm-hmm.
Yeah. So then, because you want to, when you deal with the differential equations, so you want to differentiate over the evolution of the topology. But when you have the techniques like XFEM, or when you introduced, so you cannot do that. You enrich the approximation space, but this is a discrete event of enrichment. Yeah. So we try to first solve in our case. We want to have a way how we can propagate the crack, and then we can differentiate. So we can calculate change of the system energy due to the movement of the crack front. But the another thing is a physics. Yeah. Mm-hmm. And then in the fracture mechanics, you can have a linear fracture mechanics, and then you have a nonlinear fracture mechanics when another phenomena kicks in. But in case of the ideally brittle materials, you have really simple physics. Mm-hmm. So physics, in the case of the problem which I solving, this basic problem, when you will talk about the fracturing homogeneous material, that there is no bifurcation of splitting. It's simple. Yeah, crack is propagating in such a way that it wants to release maximally energy. Yeah, so this is maximal dissipation in energy principle. So when you have a certain class of the materials, ideally brittle materials, that's work great. Yeah, you can. It's amazing. You can reproduce with this simple one thing only. So maximalize release of energy. But there is this maximal release of energy gives you idea where the crack should go. Yeah, so it's controlled direction. But you need something when you will write out the equations. You will find that you have to conserve the energy. To the conservation of energy, you add this maximal release of energy principle, and then you have to have something when the crack is propagating. And in our case, we're using a 100 years old theory, Griffith theory, mm-hmm. to do that. When the energy, Griffith energy reach certain threshold, crack is moving, so that from the physical point of view, I'm doing nothing special. So formulation of the problem is nothing special. Of course, he's using this slightly novel framework of the configurational mechanics from L-Shaby, but it's the 50s and 60s of the previous century. Then it was applied into finite elements by people like Paul Steinman, like Mie. And then what we have done, we deploy on that problem fancy approximation techniques, and we was able to propagate the crack in the continuous way that we really move the displacement. So we calculating displacement of the crack front in monolithic way with the physical apparent displacement, and this was giving us edge. That's why we can make up predictions, and the cool thing is that those predictions works because they are verified. There are some predictions I probably cannot say about them, that we make up predictions what will happen in the near future, and it happened. Yeah. So this is that something works when you make a real predictions about the future. Yeah? You don't reproduce the benchmark test experiment. You're predicting the future, truly a future.
That's super interesting. Maybe an amateur question, like when the crack propagates, how does the crack know where to propagate, and do you have to have some special element formulation in order to capture this? Like, does it have to be a finer mesh around the crack, or how do you personally do this in MoFEM?
So first thing is that what is the equation which you can write on the piece of the paper, mm-hmm. which tells you how the crack will propagate. And there is many stories, many papers about that. Someone is looking at the maximal Hooke stress. Someone is looking at the maximal principal stress, and the crack is going at a certain distance from many different ways. Mm-hmm. What we do, we calculating implicitly, we're using this maximal dissipation of energy. So we asking ourselves, you have a system which is under the stress, and then you ask yourself question, in which direction crack has to go to maximally release the energy? Yeah. So the system, so when the crack will go by certain distance or extend itself by the certain area, in some direction it will release more energy than in other.
Mm-hmm.
So this is this maximal dissipation, maximal release, because you changing the energy, elastic energy stored into in the deformation of your body into the another kind of the energy. You transform the energy from the deformation into the surface energy. So you're creating the crack area. So this is the maximal dissipation of energy decide about where to go. And then, of course, so then at that point, as you point out, that the key thing is the resolution of the stress state and strain state, and then resolution of the quality of the resolution of the energy near the crack tip, crack front in 3D. And then, so then you can do many things. One thing is just to use this enrichment, which has built, so when you work with the linear fracture mechanics, in that case, linear means harder than non-linear. When you work with the linear fracture mechanics, you have a singularity at the crack front. So then, but the finite elements, when you use the polynomial approximation base, they cannot resolve the singularity. So only way how you can capture the stresses better and better to make elements denser, denser, and denser, and denser near the crack tip, but you will never reach the singularity at the crack tip. Mm-hmm. So the only way is that extend the approximation space by enriching it by the functions which has a singularity in them. And this is what the XFEM is doing. But there is another older technique than that. It's called quarter point element. So when you add the mid node on the hex or tetrahedron mesh, and you move the mid node, so then you have a node at the crack front, and then you have from that node on you have emanating edges, and then if you have a mid node on the edge, and then you shift it by the quarter point, you will generate the Jacobian, which has a built-in right type of the singularity. Mm. So you're generating singularity, like you can imagine that you have how black hole appearing. Black hole is appearing by wrapping a space in such a way that it's singular. So exactly this happens in the quarter point element. You're wrapping this reference space of the finite element to generate the right type of the singularity at the crack tip. And this is what we are doing. And on top of that, we enriching but once we generate the singularity, we can increase the approximation space. So we locally build a bubble of the high order polynomials. So we can have a 6th order polynomial just in the vicinity of the crack tip, 5th, 4th, 3rd, and 2nd, and one polynomial when you are far away. So we're using this hierarchical approximation basis at that point. Yeah. This is what we do at the crack tip. But just to separate that, this is one thing is a resolution of the stress field near the crack front. Another is a model, mathematical or physical model. First physical and then mathematical model, which decides where to go. And there is another thing is criterion where the crack should propagate. Yeah, because not always it should propagate.
Mm-hmm. That was very, very insightful. Thank you so much, Luka, for this clear explanation. Also gives us like a physical interpretation of how to deal with cracks. A lot of people asked us before the podcast how they would delve into the finite element method. Let's say they started, they're complete beginners, and you as an expert, what path would you tell them to go? Let's say they're interested in the finite element method. Where should they start? Should they maybe even tackle their own project? Or how would you advise them? Where should they go to?
I will search for different textbooks. You can even now download the samples from the internet that check which textbook about the finite elements talks to you the best, because it's depending on your mathematical background, mm-hmm. where you studied, what you studied, and so on. And then first thing, to be honest, I will open Python, Julia, or some MATLAB, whatever you know, and try to implement the simple truss. Just solve something to work, and then maybe something with the constant thermal problem, something with Poisson problem, something very simple. But once you get the basic idea, then try to join the bigger group and then learn from them. And then it's cool, because then when you will join the bigger group, they will try to guide you, because then you ask them and they will give you a books which they know, they will share your material, they will help you somehow.
Mm-hmm. Yeah. Very, very insightful. Thank you so much, Lukasz. Regarding MoFEM, where do you see it going maybe in 5 to 10 years? What's your expectation on a wish for the future?
So biggest hope of every person who developed any code, not finite element, is to get the exponential growth. So, but with the exponential growth is this one problem, that when you look back, you see a plain line almost. But the exponential growth is in the future, which you don't see. But this is when you will see, we will be able to see into the future. You should see a steep line. So this is a development of the finite element code is not issue. The issue now is building a community. Mm-hmm. That you have followers who share your idea about the development of code. It's finite element. It's not a code. It's at the end, it's a system. When you share the culture, the certain ways how you think, how you solve the problems, how you name the things. This is whole culture. So you're creating the culture, and then, but in order that culture to happen, first thing, it has to be certain idea. It has to be certain way how you're doing those things, and others has to follow it and embrace it as their way of doing things. And then, so from very beginning, the prime importance in such development is that the people understand your code, because it's clear, has a clear structure. So then there is documentations, there is examples, and so on. This is when I want to, and to be honest, I need to another great idea. So the starting of the MoFEM was this great idea to apply MoFEM to model crack propagation in advanced gas cooled reactors. But advanced gas cooled reactors will live on the world for next 10 years. And there will be no longer reactors and that. So I need another great idea, another application. And we start to build that idea. We're looking at them called forming. We looking at the different problems like contact of the rust surface. So now we enter the era of searching of the different applications, and then I have great colleagues which work with me, 5-6 postdocs, and then they doing that. They start to apply the MoFEM to solve their problems, and they start to be true followers, and then they get the idea and they propagate and so on. So MoFEM, it's hopefully at some point in 5 years it will be not me, it will be a community, it will be something bigger than I will be a addition to something greater.
Mm-hmm. I definitely wish you all the best, Lukasz, and I hope to see MoFEM growing, and maybe we can do a short maybe a demo on my channel in the future to see actually how the MoFEM code works, and you're invited to show my followership who want to delve into FEA how MoFEM actually works, and then they can play around with it and be part of a bigger community. So now we have questions coming in from our audience from LinkedIn or Instagram. And the first question is from Stephen McEntee, who asks, programming FEM. Older codes are usually in Fortran and newer codes are often in C++, like MoFEM. Would Lukasz always recommend C++, or does he think there is still a role for modern Fortran? What about newer programming languages like Julia?
I think this is I cannot give a crisp answer. We're using C++, because it gives us our greatest flexibility. But when you're using a C++, you can restrict yourself. Using C++ in appropriate way, it become extremely messy. So using C++, you have to be restrained, and then you have to keep this culture aspect is very important. Fortran is traditionally used as a FEA is example of it, and then the Fortran has when I was using it, I'm not using it anymore. You have much less flexibility. So probability that you will make a mess with it is much smaller than in C++. But in C++, the most important thing is that you have a full power on how you manage the memory, how you allocate it. You can have the of the different containers. The strengths of the C++ coming from the ability to manage memory. So the Fortran gives you some management of the memory to think how the things are spaced in the memory. But when you go to the languages like Julia, you are completely deprived from such things. Mm-hmm. The code is managing memory from you. And there is no depending what you want to do. I think that if you want to develop the finite elements in its core, that develop the new approximation technique or new finite element formulation, to data-driven finite elements, which is topical now, you have to go into the low level, those languages like Fortran and C++. And then, in fact, I will choose Fortran because I think you have a more freedom in it than in. I will choose C++ because you have a little bit more freedom than in Fortran. And it's a language that develops faster. It has a bigger community, that there is a lot of smart people that you can find the easier resources than in Fortran. Community as well is important. When you choose the language, when it has a large community, it means that when you struggle, you have someone to ask. And the C++ has a big community. So you have plenty of people to ask, and you have a solution for everything. Yeah? Mm-hmm. Fortran has, but not as big like C++. Yeah? Julia has a big community as well, but I say that I will not choose the Julia because I working in this. I developed the code. I want to work on this low level of the finite element. So the Julia is not necessary for me.
Mm-hmm. Okay, got it. Excellent. Another question from Stephen. Research codes often demonstrate advanced features that you'd think would have valuable commercial use cases, but it seems to rarely happen. Does Lukasz have any interest in this or advice on commercializing research? What would you say?
This is exactly the point which I tried to make a few minutes back, that this is why we developed the MoFEM. We want to give a way of the researchers developing finite element code to have a path for application in the industry. And we can work as an example that we done it with the nuclear industry, so it's doable. Mm-hmm. It's hard, but it's doable. This is exactly why we try to develop MoFEM.
Yeah. And I think you made it very clear during the podcast, Lukasz. Last question from Stephen before we move to the next questions. Does Lukasz think that there should be more awareness of FEA? A lot of developers know about machine learning or computer vision programming, but never heard of FEA. What's your take on this?
Sorry for a play, but it's fast, so it will go very quickly. So when you look at you have even position at this in industry, which is called stress analysis. I think that when you talk with the older engineers, I'm thinking about 50, 60 years old people. They have this doubt. Yeah, but really, if it's make up predictions, I can make a better I can predict how I can calculate the retention wall on piece of the paper faster than finite element code, and I will trust it more because the finite element is black magic for me. But over the time, when you talk with the younger people, so my age and younger, so everybody has the finite. When you study the engineering, you have a finite element course at your uni, probably. So that's getting better. But what I think is still a big problem is this ability to interpret the results, to check. So there is no this culture of then when you run the code, refine the mesh and run it again and check if your result is changing. I am not sure if in every industry where the finite elements is used, this is checked. Really, people have really checking if their solution is correct.
Mm-hmm. Yeah, and I've seen it in the industry that some people don't. So I'll leave it at that. So
yeah, but solid mechanics is slightly better. I once speaking with the person from the car industry, which was running a simulation for the wind tunnel, said the great thing for me. So when we run the mesh with this size, we get the great comparison with the wind tunnel results. But when we make it smaller, everything is getting worse. So this is the thing that like you have the. This is what we not do. When you refine the mesh, your solution should get better, not worse. Yeah.
Yeah, I see what you mean. We have some generic questions that came in before the podcast. For example, one would be, well, we have best learn to learn FEA. We covered that already, Lukasz. And the generic question was Abaqus or Ansys. What would you choose if you had to choose between those two?
Can I refuse to answer to that question? No.
You can refuse.
I don't care, to be honest.
Mm-hmm.
Yeah.
Maybe you can say just MoFEM.
Yeah, MoFEM. I use Ansys. Yeah, some time ago just to verify my results. But people which I work, so we using at Glasgow Abaqus probably because we have a license. Depending what license you have, that is a choice.
Mm-hmm. I see. Do you have any idea the links between AI, so artificial intelligence, and FEA? Where do you see that going? Do you see it with a smile going to the future, like physics-informed neural networks, for example? How do you personally see it?
It's a funny story because when I start my PhD, I supposed to do neural networks with the finite elements. But I went to the conference and I have seen Mark Hers giving a presentation about the computational homogenization, and I said to my supervisor, I don't want to do neural networks anymore. I want to do that. And we make a promise that I will have a PhD about the computational homogenization, but last chapter will be about the finite element methods with the neural networks. And we use the neural networks. I think that is the best for that thing. We use it to solve the inverse problem. So we ask ourselves a question that we have this great model for indentation of the heterogeneous material, and we have results from the indenter, and then what is the property of the inclusion in that material. So there is inverse problem. Yeah, you have experiment, you have indentation, you measure the force, and you're asking about the property. And the neural networks are great because what you can do, you have input and output, and then you can swap the output with the input, and then you get the answer. But there is only one catch with it, that neural networks are extremely easy to use. And nowadays, even more, you have those great tools. But really, if you want to understand how they work, this mathematical theory behind them, that it's pretty hard. So if you want to go deep into neural networks, learn statistics. Yeah, you have to be a good statistician to use the neural networks in the proper way. Only if you don't do that, you will use them as a black box. But of course, they have lots of applications, even in the engineering.
Mm-hmm.
But I will not use them everywhere. So there are some problems, forward problems, where then I will use the finite element, because the finite element provide me a posteriori and a priori error estimators. And neural networks, that's hard, because the prediction depends on the data set. Nightmare.
I see what you mean. Yeah. Before I come to the closing remarks or the conclusion, last generic question we have coming in was, why is FEM so hard?
I think okay, maybe I'm doing it for too long. I think that in fact, I will answer, no, I'm getting older, and then I would say that everything where I look, it starts to look hard for me. Everything is extremely complicated, and even if you look deeper and deeper into it, it's getting more and more harder. You think that there are layers of the complexities on top, on bottom, and then always is something. So when FEM start to look hard for you, that's a good sign. It means that you start to understand it. If you learn it more, you will find out immediately that you learn this thing which is hard for you at the moment. At the bottom is harder thing even than that. And then you will go down and down, and that will never stop.
Mm-hmm. And I think a common misconception is, I think there's this common theory of when you learn something and you struggle a bit, that a lot of people make the conclusion, I struggle, therefore I must be dumb. And I think that's not the right approach, right?
In fact, in each time you learn, because when you learn, your horizon getting bigger. So you see more into the space. So the words start to be bigger, and then each time you learn something, your word gets bigger, and then everything getting more complex, because the word is complex. I think there is nothing simple in it.
Yeah. Very beautiful answer and very philosophical. Last question I have from my side. We talked on Twitter. I saw that you tweeted about meshless techniques. Where do you see them going? Do you think they're useful, or are they too slow? What's your personal take on meshless techniques?
I'm using a meshless method on a regular basis, and then we're using it. I can tell you, we have a solution which is coming from the Codaster. It has some stresses which come from the radiation complex thing. It doesn't matter. And then we have to project this solution from one mesh into another mesh. So then, and then this another mesh is constantly changing, evolving in time. So what we're doing for that, we're using meshless method. So then let's forget about this mesh on the top, and then use the meshless method. And then we're using moving least squares approximation for that, which is a great thing. Gives a smooth field that we can exploit the fact that we can have access to the first and second derivative, which is hard thing with the finite elements. That is great. But the biggest bottleneck of it is that it's slow. So the 80% of the total time is about building this approximation space for MW, moving meshless method. And then then there is a question if that method is truly meshless. So what are you using for integration? Do you have a mesh to integrate the things? And then there is this whole zoo of the methods. Sometimes if some people say that you have for free higher order regularity, but do you really need that? So, for example, when you deal with the heterogeneous materials, when you want to have stress jumps between the different materials, so meshless methods give you something very often which you don't really need. And then another thing with the meshless method is that the trick with them is on the boundary. But if for engineering problems, when you want to model running engine, or brick or building, boundary conditions is everything for you. So this is what you want to do really well. So the finite elements gives you a property, you have full control over the boundary conditions. And meshless methods are always fuzzy about that. But if you want to do SPH, for example, how to simulate how the galactic collapse, or you are astronomer, don't use the finite element, probably you will use SPH, yeah? So the different things. So I think that in engineering, meshless methods will never dominate the field. But there will be some niche applications where there is a place for them. Yeah.
Got it. So one last question. I'm sorry I said that this was the last question, but I have a last one because you mentioned boundary. Do you think things like, or methods like the boundary element method, there's a very old tool I think called BZ. Do you think this has a future, or do you think boundary element method is also like a niche application for specific things?
So I think they have. So then if you have a large space which is homogeneous, for example, acoustic problem, electromagnetic problem, antenna, boundary methods has applications. So for a long time, when you have a contact with the rough surface, so the surface, so no one can beat the boundary element method. This is because it's impossible to calculate the problem. So rough surface, that you have a surface which almost fractal resolution of the different roughnesses, and then you want to have a contact with that, and you want to have a contact. So the boundary element method was the best what we had. The problem with the boundary element method is that extending it to capture the nonlinearities, like geometrical nonlinearities, is you kill the method. Is impractical. Is because you can apply the boundary element method when you can have a fundamental solution, and you can get the fundamental solution when you have a linear problem. And there are some extensions to the plasticity. I work a little bit on the Trefts method, which is sitting somewhere in between the boundary element method and the finite element method. It's taking this idea, because boundary element method, the key idea in it is that you integrate over on the boundary. So you have a 3D problem, but you integrate over the surface. Yeah? And you have a degrees of freedom only on the surface. Big difference. When something is bulky, you can imagine how much degrees of freedom you say. Matrix which you're getting is dense, but it's not a problem because it's small. But Trefts method was sitting on the fence that you integrate on the boundary of the finite element, but not on the value of the finite element, so we can yield certain things. But the problem with the boundary element method is application for a very small amount of the problems. You cannot generalize that to large strains problem, large strain elastoplastic problem. That is impossible thing for boundary element. But contact problem when the response physically inside of the volume is linear, but you have non-linearity on the boundary only, for example, contact, perfect. Acoustics, electromagnetics, that's probably a good use for the boundary element.
So it was a very, very interesting conversation, Lukasz. I really much appreciate your time. And as a closing remark, maybe what advice would you give people, maybe last advice from an expert, and how to join the MoFEM community? What would you tell them?
Write to Q&A, contact us, and we will pull you into the loop. Yeah, and then tell us what you want to do, and we'll try to help you. And you are very welcome.
Awesome. So very interesting podcast, as I already said, and like a famous quote which said, like, the more I know that what I don't know. So I learned a lot from this podcast, especially when you think you understood the finite element method. And as you said, you're making something wrong. So thank you for proving that, Lukasz, in this podcast. And I'm really looking forward to maybe showcase MoFEM on my channel in the future. And I wish you all the best and great success.
Thank you. Bye.